Okay, between which two, so this is very important, two consecutive terms, between which two consecutive terms will the difference be, look at this, 28,088. That's the question. All right. So now this is what we're going to answer. And I want to show you how it links to what I've just illustrated. So I've got 4, 4, 8, and 16. What they are trying to say is, as you go on with this sequence, there are two terms that come one right after the other. And between those two terms, the difference is actually 28,088. That's what they're literally saying. And if you would think with me, I need you to be aware then that this 28,088 is actually a term within the arithmetic sequence that is found in this quadratic number pattern. And we're going to box that, okay? We're going to figure that out. So I've got a 0 here. 8 minus 4 is a 4. And obviously 16 minus 8 is also a 16. And then we've got 4 here. No, my bad. Is 16 minus 8 a 16? No ways. It's an 8. See those little mistakes. Okay, now this one makes sense. All right. Then 8 minus 4 is a 4. So then we know that going on and on, you will have that, and then you're going to have a term and all that. But there's going to be a point in this arithmetic. Remember, I want to write it down. Remember, this thing here is an arithmetic sequence. So when we see this difference of 28,088, we need to actually see that value as a term in the arithmetic sequence. It's going to be very tiring, very long. It will take you a lot of time. You will run out of time if you're going to try and manually find the two terms that will give you this difference. That is what I'm trying to say is, if you're going to use the quadratic sequence, it's going to take you really a long time to find out the two terms. So what we're going to do, how we're going to box it is, we're going to find the general term for the arithmetic sequence. And we know by now, yesterday we found this lovely formula, that for any arithmetic sequence, the general term can be found by using this formula. Tn is a plus n minus 1d. In this case, a is a 0 because this is the first term of the arithmetic number pattern. So that is 0. And then we just want to find the general term. So obviously the difference is 4. So we're going to end up here with a 4n minus 4. That's what we're going to end up with for the arithmetic sequence. So what this then means is that I can equate Tn to this. So in other words, I can equate 4n minus 4 to the 28,088. So that at least I know the position of this term. So that's what we're going to do. We're actually going to solve for n here. So this is that. And I'm going to divide this by 4. Then n is 7,023. You see, it was really going to take you forever, okay? So that's why you needed to use the arithmetics. Now, let's just go back here. I want you to see something. If you look at term number 4 and 5 for argument's sake, the difference between term number 4 and 5 is 13. Now, let us number the terms of our arithmetic sequence. This number 1 is actually term number 1 of the arithmetic sequence. The 5 is term number 2, the 9 is term number 3, and the 13 is actually term number 4. I'm doing this so that you can notice this key relationship. The difference between term 4 and 5 of the quadratic is actually term 4 of the arithmetic. I hope you are able to actually catch what I just said there. I know there's quite a lot of words that I'm using here, and that might be quite confusing. So let's establish this. If I go term number 5 minus term number 4, I'm actually getting term number 4 of the arithmetic. These are from the quadratic sequence, and this is from the arithmetic sequence, which is within this very same quadratic. I need you to understand this, because for us to answer this question fully, we will have to conclude the following, that, okay, term number 7023 is somewhere here. Let's maybe give an illustration. So term number 7023 of the arithmetic must be equal to what? The difference between term number 7024 and 7023 of the quadratic. I think this should make it much clearer. This is what we need to understand, which means then your final answer will be the following. The two terms that will give us the, is it 28? Yes, the 28,088 are actually term 7,024 and term 7,023. As I said, this is quite crucial. We've seen quite a number of questions being asked on this. Okay. Are you guys with me? Is someone with me? Or is there a question? I do hope that you are catching it there. Very, very important to note this relationship. Are we together? Okay, no response. Can I at least get an amen if there's an amen? There's nothing.
Amen, amen.
All right, beautiful, beautiful. Okay, cool. Now, what we're gonna do is we're gonna look at, Bulali, your hand is up. Is that to say everything is okay, or you've got a question?
Good afternoon. I have a question.
Oh yeah, go for it.
So when you said, when I'm checking the differences between the quadratic, the numbers in the quadratic pattern,
Yes.
and we're checking it with the position, the whole positioning thing, right?
Yeah, yeah.
Do we always check, um, is it the lower, is the answer always on the lower end? I'm not sure if I'm phrasing this question
Yeah, I
correctly,
think
but
I'm catching you. Yeah.
it's gonna be the lower end of the quadratic pattern. So if we have 4 and 5, we're always gonna go for 4.
Yeah, so that
Am I
term
making sense
4,
here?
yeah, I think I'm trying to get to think into what you're saying there. So
Okay.
the actual, yeah, so for the arithmetic, yeah, the actual term will be the lower one. Or maybe I should let you finish what you're saying.
Yeah, I just trying to make sense of this whole, because you're saying I'm learning this now. It's
Yes.
okay, you know what? I think I'll figure it out myself and then I'll get back to you. That's okay.
Okay, that's fine. That's fine. You can also send up a message through, on the WhatsApp.
For sure.
Right. Okay, all good. Right. Now, the next portion that we're going to discuss here, we're going to introduce you to an arithmetic series. The difference really between a series and a sequence is notation. Basically, it's how you express them. It's how you write them, how you notate them. I'll give you an example. You see, 3 semicolon 8 semicolon 13 and etc. represents a sequence. That's a sequence. But 3 plus 8 plus 13 and so on actually represents a series. You are actually adding numbers. So The principles are the same though, in terms of finding the general formula for this particular series or sequence, okay? So of course, this is arithmetic. You will notice that there is a constant difference of 5, for example, okay? So we're not gonna throw away this formula of finding the general term, 3 plus n minus 1 times d, which is a 5, and then this is 3 plus 5n minus 5. So we end up with 5n minus 2. So whether we are dealing with a series or a sequence, for as long as we are told that it is arithmetic, we will need to find, oftentimes we will actually need to find the general term. And I'm saying you can always use this formula. The only difference now is that instead of just working out the general formula, in a series, you are actually adding up a sum here. So think of this. Imagine I asked you to add up to find the sum of the series 3 plus 8 plus 13, and I say up to 5 terms. Then that means you need to actually know what the 5 terms of this series are. So if I've got 8, 5, 13, and I've got to add a 5, I think we figured that that's our constant difference. Then my next term is 18, and I got to add a 5 again. Then my next one will be 23, and I'm going to get penalized here because I have changed from series notation to sequences. So we need to be careful. Be consistent. Don't mix the pluses and the semicolons. I spoke about the fact that maths is a language, so notation is very important. How you use your symbols is very key. So now the answer, obviously, then you can go into your calculator, go 3 plus 8 plus 13 plus 18 plus 23. And the answer here is a 65. So it is very easy to do this with few terms. But imagine I asked you to find the sum up to 127 terms. Then that's going to be troublesome. You will try and add this. Depending on the type of calculator that you use, your calculator might say, I'm out of memory. I can't do this anymore. So we need a smarter way, a quicker way. And this is the beauty of mathematics. What we do, we try and make simple things a bit complicated so that whenever we come across complicated stuff, we can really solve them easily so. And that's what we're going to do. So I'm going to tell you a little story here, which I hope will inspire some of you to become inventors of solutions to the mathematical problems that we have in the 21st century. So this dates back to the early years, ancient years, I suppose, when none of us were born yet. But there was a mathematician called Gauss. But this was before he became a mathematician. He was just in a classroom like you are today. And because there were no calculators back then, the teacher wanted to push some admin, as we would want to, and we would want you guys to keep quiet. If you can't keep quiet, we give you work so that you're busy. So that's what the teacher said to Gauss and his classmates. She wrote on the board and said, listen here, students, I want you to add all the numbers, natural numbers for that matter, from 1 up to 100. That's what she said. And because there were no calculators, she really thought to herself, if I give the students this type of work, it's going to take a while for them to actually come up with an answer. So it's going to take time. And because it's going to take time, I will be able to finish all my administration. Then, to her marvel, Gauss finished this in about 5-10 minutes, but in a very short space of time, he was done adding up. And then she became curious, obviously. How on earth did you do that so fast? And this is what Gauss did. And we're going to use the approach of Gauss to actually derive a formula for ourselves to find the sum for any arithmetic number pattern. So this is what Gauss said. Gauss said, well, let S be the sum. So letter S for sum. Let S be the sum of these natural numbers from 1 up to 100. That's what he said. Then he said, well, I'm going to rewrite S. I'm going to rewrite S as follows. 100 backwards. In other words, he rewrites it backwards. So he starts with the smallest number in the first instance up to 100. Then in the second instance, he rewrites the same thing, but he starts with the biggest number going downwards. Then he says, I'm going to start with 100, and then I'm going to go 99, and then I'm going to go 98. And if you think with me, it means he ended with a 1 there. Then what he did, remember back then they would do column addition. Then he started to add. So if I add here the left-hand side, I will have 2s. S plus s is 2s, right? And then what would happen here if we add all these numbers? Look at this. 1 plus 100 is 101, right? 2 plus a 99 will also give you 101. 3 plus a 98 will still give you 101 until you add the very last one, which will also give you 101. But then Gauss thought to himself, but how many 101s am I adding here? And he figured, oh, I'm adding 100 numbers. So I'm surely adding 100 101s. So if I'm adding 100 101s, it means I can just multiply 100 by 101. And then this is 2s. But because I'm solving for s, I can divide both sides by 2. Then I will get 50 times 101. And if you like, then you will notice, well, 50 times 101, that could have been simple to multiply if you do the following. Let's all pretend we don't have calculators. 100 plus 1. Now, we all know how to multiply in tens and hundreds, right? So 50 times 100 would then obviously give you what? 5,000. And then 50 times 1 will give you a 50, which means S is actually what? 5,050. And so just like that, Gauss was done adding all this up. And the teacher marveled to herself, how on earth did he do this? And so he showed her this. He showed her this. And just like that, because of this little exercise that took place in a classroom some years back, today we are able to calculate the sum of any arithmetic number pattern. Now, if you caught this, I'm about to go abstract now. I'm about to use letters. In other words, I want you to see that we're going to use the exact same thing. We're going to do the exact same thing, but we're going to come up with a beautiful formula here. Watch. So let's write an arithmetic series, an ordinary arithmetic series S, where A is the first term. We learned this. And then obviously if D is the constant difference, then the next term is A plus D. And then after A plus D, I want you to think, let me just pause a bit there and then maybe write down, yeah, the first 3 terms and the last terms. Okay. So if you're thinking with me, your next term should be A plus 2D. And obviously, this will go on and on and on. Now, yesterday, I said something very important. And what did I say? I said to you, for any arithmetic sequence, in fact, for any sequence really, the last term can always be what? The general term. I said the last term is always Tn. And because this is arithmetic, we must remember that Tn is actually A plus n minus 1 times D. So this is a principle that we established yesterday. Guess what? It is coming into play today. And we saw why this is the case. All right. So that's what I'm going to do. Let's do what Gauss did. Let's write this backwards. Okay. So if we write this backwards, then obviously I'm going to start with a Tn here. And I want you to think with me then. If we started with 100 here, then the term that comes just before 100 is a 99. But what did you do there to get the 99? You subtracted a 1. Now, this is not by accident, because if you look at our original series, the constant difference is actually a 1. So with that being said, I hope you'll agree with me then that the term that comes just before Tn will be Tn minus the constant difference, which is a d. This is very important to note. So that will be the one term. And then obviously here you are subtracting the difference twice, so we must have that. And then we can go on and on. Sihle, talk to me.
Afternoon, am I audible?
Yes.
Sorry, may you please just clarify why we're using Tn? I'm just a bit confused.
Okay, Tn represents the last term. I don't know if you joined yesterday's lesson or you are able to catch up on this. In any sequence, the last term is equivalent to Tn. In any arithmetic sequence, yes. Are you with me? So Tn here is like my 100 here. Remember, the 100 here was the last term. Okay? And that's always Tn. Okay.
Oh, so then
Yes, go for it.
for you to be able to get 99 there, you subtracted the 1 from the 100.
Aha, correct. You just subtract the constant difference. So the constant difference was 1. So we subtracted 1 from the 99. We subtracted 1 again, etc., etc. Because this type of series was increasing by 1. Are you with me?
Thank you.
Okay, well done. Good question. Now, in this case, our sequence is increasing by the letter D. Each time we are adding D. So that is what is happening at the top here. At the bottom, we have to keep subtracting D. So we started with the last term Tn. Because D is our constant difference, we have to keep subtracting that. Bulali, you've got a question?
I was going to ask if our sequences always have a beginning and end value.
Not always. Series don't always have, unless I just tell you I'm just interested in the first 100 or in the first 10 of few. So you will notice after we have derived this formula is going to be very generic, because one of the examples which we will do will be calculate the sum of the first 50 terms. Okay. When we talk about the geometric sequence, which will be our next lesson, or the geometric series, you will realize that the geometric series tends to behave differently. In some instances, the geometric series goes, it diverges, like the numbers keep growing up. But in some cases, you'll realize for the geometric series, it becomes limited to a certain number. And we will talk about that. But generally speaking, like an arithmetic series, actually think of it this way. If you were to start counting today in ones and go 1, 2, 3, 4, 5, etc., will you ever stop counting? No, you're not going to stop counting. You're going to get to hundreds. From hundreds, you're going to get to thousands, 10,000s, etc., etc. So it's infinite. So number patterns, especially arithmetic number patterns, can go on infinitely. So it just depends on you where you want to stop. In the case of Gauss and the teacher was just interested in the first 100 numbers. I hope I have found you there. All good?
Thank you.
Okay, awesome. So now, as we saw, then that means here we're going to have an A, because A was our first term. Just as we did here, 100 and 1. 1 was our first term, 100 was the last. I hope you see that pattern. Here, I've got the 100 and the 1. The same thing here. I've got the 100 and the 1, just written vice versa. Okay, so that's what we've got here. And we're not going to do anything different from Gauss. We're going to add these up. We're going to add these up again. And you notice, oh, by the way, because we are using n, this is generic, we don't have a finite number thanks to Bulali's question there. I must actually use Sn because I don't have a fixed number of terms here. So if I add up here on the left-hand side, this is 2Sn. And I want you to note what happens as we add up the first two here in this column. We will have A plus Tn. And if I add up the second, the same thing is actually going to happen. As you notice, a negative D and a positive D, or positive D and a negative D, will obviously eliminate each other, and you will definitely be left with A plus Tn. Okay, let me just try and write that. So if you go A plus D plus Tn minus D, this is what happens. D subtracts D, and you are left with that. And you will notice that is actually the pattern that follows right through. Look at the third one here. You have a positive 2D and a negative 2D. So that will be the same order here. And this will go on and on up until this last pair here. Now, classical question. Remember what Gauss asked here. Gauss asked a very important question. How many of these 101s do I have? Well, he has 100. In our case, how many of these do we have? Let me hear if someone is thinking with me here. I want to hear the answer from you. How many of these do we have?
Tn.
N, yes, let's Tn, I could sense what you're saying. It's N of them, remember? And it comes from the fact that we're working with Sn here. So very good. We have N of these, which means then, like Gauss, we can work out a product here and say we are actually multiplying N by A plus Tn. And obviously, this is equal to 2Sn. Then what I will do is I will divide by 2 both sides as Gauss did. And so you could write this as A plus Tn all over 2 like that. Or you could write it as N over 2, in other words, half N times A plus Tn. These are exactly the same statements. Never mind me using square and round brackets. But for consistency, maybe let me just stick to square brackets. Okay, so these are exactly synonymous. Now, what I'm going to do is very simple. I'm going to substitute A plus N minus 1 times D in the place of Tn because we know the formula for Tn. So instead of keeping Tn, I will then substitute and say, well, Tn is A plus N minus 1 times D, like that. And then if I simplify what is inside the brackets, that is adding like terms and so forth, A plus A is 2A, and then this will be N minus 1 times D. This here is your final product, your formula for calculating the sum of any number of terms in an arithmetic series, whether it's 100 terms, whether it's 50 terms, whether it's 1,000 terms. Remember that 1,000, that 100, that 50 is actually the value of n. So as per Bulali's question, we can ask you for any number. So when I say calculate the first 99 terms of a given arithmetic series, it means you're going to have to do the following first. Find A for that series, find D for that series. And because I would have said 99, you will then substitute 99 in the place of n. And just like that, you will have the sum. I want you to take note, though, that in a case where I give you the last term of the series, instead of using this version of the formula, you could actually modify this version of the formula. And in the place of Tn, do the following. A plus L. Where does this come from? It comes from this red block here. We said L is equivalent to Tn. So once again, that's all I have done. I have replaced L with Tn. So there's two ways actually we could replace Tn. We could put A plus n minus 1 times D. This is where we don't know the last term. But if I know the last term, instead of using A plus n minus 1 times D in the place of Tn, I can simply use the last term. So formally speaking, here is our two official formulas for calculating the sum of n terms in any arithmetic series. Number one, Sn is equal to n over 2 into a plus L, and this is only if we know the last term. When we do not know the last term, but we kind of have an idea what the first term is and what the constant difference is, then we can use the formula Sn is equal to n over 2 into 2a plus n minus 1 times d. These are the two standard formula for any arithmetic series. So I will go straight into examples. I'll take one or two examples, and then we look at how we can apply this. Okay, so let's take, it's an arithmetic series. So given the arithmetic series, what is the series? Look at this. And we have negative numbers in this one. So this is a very good one. I like this question actually. -1. Remember, in a series, there are no semicolons. You will either be adding or subtracting. So look at this. And I keep subtracting up to -16. So again, let's not be stereotyped and think that we will always have pluses in a case of a series. Guess what? We can also have subtraction. So if we note here, you will realize that you actually have the last term, which if you like, you can indicate as Tn as well. So obviously the question is, or let me write the questions. They are not so obvious. The first question here is, we want the number of terms. So determine number of terms in the series. So actually, how many terms are here? And then the second question will be, calculate the sum. So determine or calculate the sum of the series. Sum of the series. So we will use this beautiful principle to actually find the number of terms in this series. So let's look at the solution. For the first question, we will use the fact that Tn is always equal to the last term. What is the general term for an arithmetic series or sequence? A plus n minus 1 times d. And what is the last term? -16. Do I know the a? Yes, it's a -1. Do I know the n? No, that is actually what I am looking for. Do I know the constant difference? Yes, I can figure that out by checking whether I'm getting the same value when I say T2 minus T1 and T3 minus T2. Now, I'm gonna do this and I'm gonna show you actually how your calculator can be useful. And please, again, don't feel like I'm insulting your intelligence here, because this is where errors happen. We see a lot of errors here. So please, this is what you need to be aware of. Your second term is -3 over 2. And to find the difference, you are subtracting. The word difference means subtract. Take note that you are subtracting a negative number. So if you will type this in your calculator meticulously like this, I promise you, you're going to save yourself errors from making errors rather. And in saving yourself from making errors, you are securing marks. Marks on sequence and series are really easy marks, but students often lose out on these marks because of careless errors. So if you've got a calculator to protect you, if you can, then do that freely. And you will notice, even if you take a -2 and you subtract that -3 over 2, you're still getting the same number. Now, why am I doing this? Remember, oftentimes a math student rushes through a paper. A typical math student rushes through the paper. And because they rush through the paper, sometimes when they type in stuff in the calculator, they type stuff incorrectly. So what I do or advise students to do at times is do this thing of constant difference twice to just make sure you actually get the same number and you are on the right track. You are not making a mistake that will be costly. Okay, so we have established that the constant difference is -1/2. So I will substitute that. And this is equal to -16. All we got to do now here is to simplify this, and then we're done. So there's two ways to do this. Of course, the typical one is to FOIL in or distribute, not FOIL, sorry, distribute. So if I distribute here, the -1/2 times n will be -1/2 n, or if you like, -n over 2. So please beware of the fact that a -1/2 n is the same as a -n over 2. Why? Because we see n as actually n over 1. So when you multiply fractions, you multiply numerator by numerator and denominator by denominator. So that's basically it. Okay, negative and a negative is a positive. 1 times any number would be that number, and this is equal to -16. And I know that most of us here hate fractions. We don't like stuff in the denominator. So we're going to multiply by the LCD right through. Our LCD is a 2. So I'm going to multiply this 1 by 2. I'm going to do the same thing here. I'm going to do the same thing there, and I'm going to do the same thing there. Obviously, where there's a 2 in the denominator, they will divide each other. But then this one here will become a -2, and I will have a -n plus a 1, and this will be a negative, I want to believe it's -32. Then the next thing is just finish up solving for n. If we clean up on the left-hand side, we're going to have -n minus 1 is equal to a -32. Then what I will do here, I will keep the -n and I will add a 1 on both sides, and this will be a -31, which means that n is equal to 31. And this answer has to make sense because in number patterns, whether you've got quadratic, geometric, or arithmetic, we're dealing with natural numbers as far as term positions are concerned. So it means now we have 31 terms in this series. And the second question, which requires the total, the sum of the series, it then means we are looking for S31. But since I know the last term, there's no need for me to hustle that much. I can just go 31 over 2 into A, which is the first term, plus L, but that is that. And then we can then do this in the calculator. You can write it as a fraction. And guys, fractions are numbers, so it is okay to get a fraction as an answer. I have Kumvana with a question. You've got a question or a comment? Go for it. Kumvana, are you there? Just make sure you are unmuted, and then you can.
Yes. Yeah, I was unmuted. I wanted to ask, so for the arithmetic series, the formula, do we get a mark for writing the formula and for substituting into the formula?
So often what happens is they will do like this. So for formula and substitution, they will give you a mark. So when you show the substitution directly, that shouldn't be a big deal. But then sometimes what happens is when you make a mistake, they will actually check, did you write down the formula? So depends on how meticulous you want to be. If you are a lazy mathematician like myself, you will kind of substitute directly like that. I promise you this will be probably worth 2 marks or even 1 in some cases. So It's not a big deal if you don't write the formula explicitly, but I know it is very helpful for some students to actually write the formula so that they see what they are substituting. Sometimes your mind gets all over in an exam because the invigilator said 5 minutes left or 30 minutes left and you are left with so many questions. So writing down the formula, although there might not be a mark for it, it is very helpful because it eliminates unnecessary errors. Okay.
Okay. Thank you.
All good, all good. Right, so that will be the sum in this question. And I want you again. Yes, someone is there. Nhlanhla.
Yeah, I don't know if I'm the one who's wrong, but like, didn't you transpose the -2 to the right-hand side?
Where? Here? From here to there?
Yeah.
Oh, no, what I did is I added the -2 and the +1 and I got -1.
Oh, okay.
Yes. Then only here, then that's what I did. Yeah. I just added like terms on the left-hand side. Yeah, that's all. Happy?
Yes,
okay.
yeah.
All right, perfect. Okay, cool. Let's do another one. Let's make it maybe a bit interesting. Let's do another type of question. Still on the same concept. We're just exploring the sum of an arithmetic series. Here's another one. How many terms so there's a different way again of testing the concept. How many terms of the arithmetic series the series is 8 plus 13 plus 18 and so on will add up to a 1,700. Well, that's the question. How many terms in the series will add up to 1,700? So obviously it is very important here to note that the 1,700 is actually the Sn. It is your sum. So what are you doing? You are given Sn, you are looking for n. You see, just like we had in the normal sequences, sometimes I can give you a term value and ask you for the term position. It is the same thing here. I can give you a sum and ask you actually how many terms added up here. So because I don't know the last term, the formula for Sn with an L will not work. But the formula that will work in this case is Sn is equal to n over 2 into 2a plus n minus 1 times d. And I'm looking for n. I know that these must add up to 1,700. We're solving for n, so we keep n as it is. A is an 8, and then we go n minus 1 times. I hope you all note that the difference is a 5. And then close our brackets. Let's just clean up quickly the brackets. Again, as I said, because some people really get intimidated by fractions, since this is a product, since this whole thing is a product, you are more than welcome to multiply by 2 both sides so that you get rid of that fraction. So this will just be 34,000 on the left, and then you are left with n, and then you can work out whatever is in the brackets. That's a 16, and then this is a 5n minus 5. So that way you have kind of saved yourself from the nightmare of fractions. Before you multiply in, please, whenever you've got a bracket, something inside brackets, and there's something outside, before you multiply in, it's a good practice to check whether there are like terms or not inside the bracket. And as you can see in this case, I do have like terms, the 16 and the 5. So I'd rather start with the 16 minus 5, which is, I think it's an 11, that, and then this is 34, or rather 3,400. The Americans would say 3,400. Anyways, now let's multiply. This is 11n, and this is 5n squared. Be careful there. And then 3,400, and then we would go standard form. It's a quadratic equation. Remember in lesson 1, we spoke about this. Quadratic equation means you should anticipate at least 2 solutions, okay? And we're not gonna try and shine up and factorize here. You're gonna waste your time. We have a quadratic formula for a reason. So you will write for me that n is the following: minus 11 plus minus. Zwane, go for it. I'm listening. You can ask your question or make your comment, and then we'll hear what. Yes.
My question is, when you take 3,400 to the other side, won't it be negative?
Oh, yeah, of course. Of course. What a fatal error I've made there. Thank you for that. Of course, that must be negative. Thank you. And I guess that was probably the reason for many other hands. Well done, guys. At least you are engaged. That's good. 2 times a, which is a 5. Okay, so you just need to show this step, then therefore you can go n is equal to, if you do this correctly in your calculator, you will get a 25 as one answer, and then it's a quadratic, so write both answers, please, and then minus 136 over 5, but we know this solution here is not applicable, therefore the sum of the first 25 terms is 1,700, or there are, if you like to answer this fully, there are 25 terms. That will be the applicable answer. All right, all good? Then maybe another illustration before I give you exam level type of questions. Another illustration to do here that might be helpful is to do questions like this. So, oh yes, Sihle, you've got a question. Come through.
Oh, so how would you allocate marks for this question?
A mark allocation. Okay, Sihle is in the manual already. He wants to know how many marks am I getting. Well, probably for the correct formula as well, with the substitution will give you that. And then some I've seen, especially with the Department of Education, IEB doesn't really make it a big deal, but the department would always credit you for writing a quadratic equation in standard form. They will always credit you for that. And then sometimes, and this is the reason I say write both, I've seen a mark being allocated to both answers here, and obviously for making the right choice they give you a mark as well. So 1, 2, 3, 4, 5. Some examiners, again based on where marks are needed, some may feel they want to give you a mark for simplifying here, but since well you do a lot of algebra and all that, some may feel you don't need to be given a mark for that. So I would say plus minus what, 5 marks. Right, that's that. And sometimes they actually give a mark for that quadratic formula. Sometimes they do that. Okay, so that is why we always say, and this is how they justify it. You know, if you read your exam instructions, there will always be that instruction that says, show all your working. Okay, show all steps. All right, or it is in your best interest to show all working. Okay, because you don't have the memo. You don't know what the examiner is actually really quite interested in when they mark. So it's always good to be on the safer side, and that is showing enough working as you can. Right. Then the next one, the last example for the day really, we have another arithmetic series. So, oh, Sihle again. Yes, Sihle, go for it.
Sorry. One more question.
Yes.
You see, when we were started, we wrote the original formula for the sum, right?
Yeah.
We wrote down the original. So when we're doing quadratics, we don't need to write down the original quadratic formula.
Yeah, because often in the quadratic, we ask you to find that formula. We ask you to find the general term like A, B, and C, what they are and all that. So that's where actually the marks will be. Yeah, and you will realize
Okay.
in high school level, we don't actually do the sum for a quadratic. It is there, it does exist. Those who do further studies, maths and all that, they get to have that experience, but we don't do it here in core maths. We just stop at the arithmetic and the geometric, but there is a sum for a quadratic number pattern. There is a formula for the sum of a quadratic number pattern. All right.
Sorry, I think you misunderstood me. I'm asking, since we use the quadratic formula, don't we have to write down the original quadratic formula?
Oh, my bad. You know what I'm thinking? I'm thinking when you're saying quadratic, I'm thinking quadratic sequence because we're doing sequences. No, you don't have to write the original quadratic formula. You can just show the substitution directly. And while at that, let me repeat what I said the other day. The quadratic formula is given in terms of x in the information sheet, but we are not solving for x here. We are solving for n. So take note that I have actually used n. Yeah, thank you. You don't have to. You can just show the substitution. Okay, all good, Sitle? Okay, given, we're going to continue here. Given an arithmetic, the last example, given an arithmetic series, a different question though. Watch this, -4, -1, then things change to a +2, and then we go on adding. Check this question. The question says, determine or calculate the smallest value of n for which Sn is greater than 300. That's one. And then the other one is, this is a very good question. Determine the greatest number of terms that can be added together if the answer must be less than 100. Very good, noble questions presented here. So what we're going to do to solve this out, and often what students often do, they take the formula for Sn and they say greater than 100. Look, the easiest way to go about this, so no overthinking, just keep calm. For question A, if I want to know the smallest value of n for which the sum, by the way, when you see Sn, sum of n terms, for which the sum of n terms must be bigger than 300, then for me, it will make sense to actually find the n value that gives me 300. Okay, the n value, in other words, the number of terms that I must add to get 300. If I know the number of terms that I must add to add 300, then surely I will be able to answer this question. Okay, so that's how we're going to box it. So now we're looking for n, obviously, so we don't have the last term, so we're going to have to use the other formula. And again, was it Sihle? Take note, I am not rewriting the formula, I'm just substituting right away. This step is also not that important. It is just for me to kind of know what I'm doing here. Then n minus 1. And again, be careful, please. You are looking for the constant difference here. The constant difference, you will be doing -1, subtract a -4. And this gives you a +3. If you've got to use a calculator to avoid errors, so be it. So the constant difference here is a +3. and this is equivalent to 300. Once again, I want to get rid of fractions, so I will write this as n into -8. I'm just simplifying the bracket here, what is inside the brackets, and I will multiply by 2 to have a 600 here, and I'm going to add like terms inside the brackets. That's a -11. I don't know why I have a -3n there. It should be positive. So I'll have 3n minus 11, and I'm multiplying this by n. This is equal to 600. Look at this. I've got another quadratic equation coming up. 3n squared minus 11n minus 600 is equal to 0. Standard form is always important, and it's advisable that you do that. Then the next thing is you go into your quadratic formula and you're going to substitute, right? It's a negative. Take note, the b is negative. And this is where using brackets for substitution will start paying off. Plus minus. And I'm going to show you another common error in the quadratic. If you don't use brackets, you're going to do this, right? And this is incorrect. Okay, you can check it in your calculator. -11 squared is very different from -11 all squared. Okay, this here will give you a -121, but this here will give you a +121. Once again, I just want to stress how important it is to use brackets whenever you substitute. Please make it a habit, whether you substitute in positive numbers or negative numbers. Let that be your standard procedure. Okay, then this is 2 times 3. Once you have shown the substitution like this, you can go straight into your calculator, right? And then we get the following. Watch this. I get 16.09 as my one answer. And my other answer, if you will look, my other answer is, watch this, -12.43. Please confirm. Okay, so guys, we obviously know this number is not applicable, but what does this 16.9 mean? Okay, we know n must be natural. It means that, okay, if I take n is equal to 17, because 17 is the next natural number after 16.9. If I take n is equal to 17, then definitely I'm going to get a sum which is bigger than 300. I'm not going to get a sum that's smaller. It will be definitely bigger than 300. So this is where interpretation will be very important and useful. I actually want to give you question 2 as a homework. And then when we meet, we're not going to meet tomorrow. We're going to meet on Sunday. That's going to be our next meeting. When we meet on Sunday in the morning, by the way, that's when we will have a look at this and do corrections. Some of you have been good in sending solutions. Those are welcome. Sorry if I've not been able to give you feedback, but we will always kind of start with reviewing a homework problem whenever homework is given. So to close this off, let's have question B as your homework problem. Okay. No questions? If there are no questions, then we're going to close it off here, guys. Cheers.